Hi everyone. This is the continuation of tutorial 7, and I'm going to go over the concept of Laplacian. You notice that there are quite a few problems in your tutorial sheet 7, which are devoted to calculation of Laplacian operator. Of course, I did explain to you one example in the at the end of previous tutorial 7, previous recording. But it turns out it's not enough because you probably noticed that some of the assignments look very strange. They require you to make the notation, denote certain expression by R, by letter R, and then to calculate Laplacian in terms of R. This problem sounds a little bit tricky, and it is tricky. I need to check my camera first. Yeah, it's a little bit blurry. I need to do something about it. Now it looks better, definitely better. Okay, so I'm going to write with this big pencil, so probably, so it's okay. So what we are going, so the whole tutorial, this tutorial 7a, which I call 7a, will be devoted to this situation. When you are faced with the task of calculating Laplacian for a function of 3 variables, but they ask you to do this notation first. Okay, but you know what? So the whole point will be about Laplacian, the whole topic of this tutorial, Laplacian of a function phi, which is has variables x, y, and z. It's still blurry. You can see it's blurry. Oh no, it's fine. It's fine. It's just wobbling a little bit. I should try out more. Okay, I don't know. Okay, so but you know what? First of all, we need to discuss partial derivatives and their notation. So let's make the first part just introduction, intro. And here I'm going to talk about partial derivatives. Partial derivatives of the technique of finding them, derivatives. And also about notations. Oh, very bright color. Okay, so let's just remember that, let's discuss chain rule first. You remember this chain rule from the differentiation. So let's imagine that we are dealing with function not f of x, but f of g of x. So this is like a complex function. And in this case, your function f is dependent on j of the internal function, and then internal function is dependent of a. So as a result, of course, the whole function f has variable f. So this is the beginning, this is a function, and this is its variable. And your task was to find df, no, notation is wrong, df of dx. This is notation for derivative. What was your chain rule? You needed to take the derivative of f with respect to j first, to the internal function, and then times the derivative of j of the internal function with respect to x. So it was like traveling down this diagram. So you started with f, and then the first section of your road was to get from f to g. And in this case, you write df over dj. So derivative of f with respect to j. And the next step of your journey, the second leg of your journey, was from j to x. So in this case, it's dj over dx. So this was your chain rule. But you know that this notation is quite bulky, I think. Instead of df or dx, of course, you used prime. But you know, in this case, it's better to use the variable here to highlight the thought that you are differentiating. Prime means differentiating over variable x. So the whole rule, chain rule, can be written in much convenient notations. So f prime over d with respect to j, and finally g prime x. So since now I'm going to use these short notations, because otherwise all my formulas will look so big and so daunting. And similarly, let's take another example. So this was the example number 1, the very first. It wasn't even the function of multiple variables. It was a function of one variable. So, for example, you could have faced even much more complicated function. So f the internal function, j is the next function, and there is also the innermost function h or x. In this case, you can write diagram as f, then you go to j, then you go to h, and finally end up having your variable x. So f is eventually the function of x. But to take the derivative of x, of f with respect to x, you need to view your journey from f to x, according to this diagram, as consisting of three sections. So the first section you need to get from f to j. It means f prime with respect to j. Then the next leg of the journey is g prime h. And finally, the final section of the journey, h prime x. So that's it. That's how this chain rule used to work for ordinary functions, not functions of many variables. And now let's call it subtopic number 2 inside this thing. So we can discuss partial derivatives for the functions of many variables. So let's consider f is dependent on 3 variables in this case. F is dependent on 3 variables. You can still write the diagram. So f is directly dependent on 3 variables. This time, multivariable functions they're called. It's still not quite sharp. Image, I don't know how to improve it. Okay, so in this case, you are dealing with not only one derivative, but with 3 derivatives. So it will be df over dx. Look at the notation. When you are dealing with the partial derivatives, the d should be this one, this style, unlike compared to the previous style. This was the function of only one derivative. That is why they draw the d like a right. But here d is like a round shape. And you know what? But I'm going to use the same notation which I introduced you before. So f prime x. In the case of df over dy, you can use this notation, f prime y. And finally, of course, df with respect to dz will be rewritten f prime z. This is a very nice notation. And moreover, you will also have to deal with second derivatives. So the second derivative, the notation for the second derivative was especially daunting. Look at this. And what I'm going to do, but you know, the definition of the second derivative was, let's just recall the definition. You needed to take the first derivative, which you calculated before, and to take another derivative with respect to the same variable x. But you know, it looks very bulky. So instead of writing the second derivative in this way, I'm going to write it as z2 prime xx, much easier. And the definition itself, this definition can be rewritten in a very explicit way. So you are taking the first derivative, z prime x, and taking one more derivative of it. So I think it appeals to everyone to be able to rewrite our notation in this way. And of course, maybe you remember that you were, no, I'm not going to talk about it. I'm not going to talk about anything else. Okay, so, but what about the chain rule? Sometimes it happens so that this function of 3 variables can have this intermediate function j inside it, or maybe even several functions. Chain rule, let's write it down, chain rule. That's what we are going to do now. We are going to apply this chain rule. That is why now we are preparing for this. So what is about chain rule? Chain rule, you need chain rule when your function is not is still dependent on these 3 or maybe 2 variables. It doesn't matter. The number of variables doesn't matter. But there is an intermediate function. So first, your function is dependent on g, and only after that it depends on x and y and z. So diagram should be written like this. First, you need to travel to j from f, and then there is a forking here, x, y, z. So that's how this all dependencies look like. And that is why when you need the first derivative with respect to x, you need to realize that this is the start of your journey and this is the end of your journey. So you need to get from f to x. And you can see your journey consists of 2 sections. And that is why your formula for your partial derivative will consist of two terms. So this is the first term, f prime g times the second section of this journey, g prime x, and so on. Let's write down for x f prime y, for example. So this means that your journey would look like this. Your track will look like this. So f prime j, again, this is our first section, but the second section would be 4 prime a or 4 prime y. Oh, no, g prime y, sorry, and so on. So now you know how to deal with these chain rules, with these diagrams. So the best idea is to write down the diagram showing you all the dependencies from the beginning of your function and to final variables. And after that, all these formulas, all these chain rules will be written in a very easy way. Okay, so it was introduction, as I said. Now, let's start preparing for our situation. Let's call it topic number two. We are getting closer to our problem. So topic number 2 will be exploring this function R. Exploring function R, which is given by formula, R is equal to square root of x squared plus y squared plus z squared. In some of your problems, you are given this assignment quite explicitly. They give you a function of 3 variables, phi. It's traditionally denoted as phi. And they ask you to find the Laplacian, which consists of second derivatives, as you know. But they pointed out to you explicitly that you should do this, this notation. How to deal with this situation? First of all, we need to explore this function thoroughly. So let's write down this function again, because this color is too bright. So this function is this. And the reason why they give you such a strange problem is that this Laplacian is very popular in very many applications, including physics and other fields of science. And that is why this expression has quite explicit meaning. It's actually the radius vector or some point in 3D space. And that is why in these applications, it's super important to be able to calculate this Laplacian in a very easy and efficient and quick way. And that is why for you, it's a good training, like before using your knowledge in applications. It still becomes blurry from time to time. I don't know what to do it. It's so sensible to the slightest movement. Okay, so let's explore this function. What do I mean by exploring this function? Let's explore its first derivatives and the second derivatives, because that's what we are going to deal with when calculating Laplacian. So let's start calculating the first derivative, r prime x. As I said before, it's equivalent to dr over dx. I don't like this notation because it's getting too long. So you can see that this is a complex function, of course, and the chain rule should be applied because the external function is square root of something. This can be called j. An internal function is another function. But you know what? You know this rule pretty well. That is why I'm not going to write diagrams for you. Or maybe, yeah. Maybe why not? I don't know. I think that you already got a good training with the calculating chain, with applicating chain rules. So no, I better not do it. The only thing I wanted to remind you is to how to take a derivative of some square root of x. Of course, you can rewrite square root as the power of 1/2. So this is actually x to the power of 1/2, and apply the very well-known formula. But you know what? The square roots are so popular in mathematics that maybe it makes sense to write out the separate formula for the square root. So let's try and use it. So your external, j of x is square root of something. So you need to take, according to the chain rule, you need to take a square root of the derivative of this square root. So it's according to this formula, square root of x squared plus y squared plus z squared. And then you need to multiply it by the derivative for this external function. Let me do it in every detail. So external expression is this one, and you need to take prime of x. Not very good handwriting. So this the derivative of this guy is 2x, of course, and 2x you put it here, and 2 and 2 cancel out. So you end up having x divided by x squared by y squared plus z squared, and this is r prime x. So this is our first derivative. But you know what? The beautiful thing about functions like this, that this function is actually symmetrical with respect to all the variables x, y, and z. And that is why you don't need to rack your brains anymore as to how to calculate the derivative with respect to y. You can just use this expression and substitute x with y, because if you substitute this variable here, that's where it changes, and it doesn't affect this expression at all, because it only means that you are swapping these terms, but it doesn't matter. So in other words, it's y divided by the square root x squared plus y squared plus z squared, and of course the same goes for the third derivative, third partial derivative. R prime respect to z will be just z here, and the contents of square root are the same. Okay. So it all looks quite nice, but quite bulky at the time. But you know what? You can view this like a system of three equations. What if we try to square both sides of these equations and then add up together these expressions? So the first, let's imagine that we took to the power of 2 each side of this equation. So the left hand side will be r prime x squared, and then I'm going to add all these three equations. So this, and the second will be r prime y squared, and finally r prime z squared. So this is how the left hand side of our result equation will look like. And also we need to square these expressions and add them together. So the first expression will be x squared divided by, just without square root, x squared plus z squared. This expression should be squared as well. Let's rewrite it. We will get this expression. And finally, z squared divided by the same denominator. As you can see, you can add up together all these expressions, and you will end up having just one. So we got quite a nice formula, quite a nice relationship between the first partial derivatives of our function r, which is the square root of this expression. So okay, so it will be very useful for us when we'll start calculating our nabla Laplacian. Okay, now it's time to explore the second derivatives, of course, because Laplacian, unfortunately, is not about the first derivatives, it's about the second derivatives. That is why let's explore what is r prime prime xx, which is the second derivative of our function r with respect to x. Let's recall the definition. According to the definition, you need to take the first derivative with respect to the same variable and differentiate it once again. So let me copy r prime x here. So r prime x was here. Do you remember this in the frame? So it's quite a fancy expressions, but we can't do anything about it. So this was our the internal expression, and we need to differentiate it with respect to x again. Okay, let's do it. So how can we do it? Let's pretend that we don't know that these guys are, not to make things too complicated maybe for you. Let's do it just like as it is. You need to know the derivative of the fraction u divided by v prime. What is this derivative? This is u prime times v minus vice versa minus u v prime and divided by v squared. So this was the formula for taking derivative from the fraction, from the ratio. Okay, so we need to apply. So our u is here, this is numerator, and v is here. Let's do it. Oh, maybe I don't have enough space even here. Okay, I'll try to squeeze it in. So the derivative from of the numerator with respect to x is just 1. Maybe I can write it 1 times. And the denominator should be written here unchanged. So this is square root of our expression. Okay, minus. Now vice versa. You need to rewrite this guy x. And you need to take the derivative of the square root. But you know what? We already did this derivative here. We can just substitute it here. So the derivative of the root will be x divided by the same square root. So I'm using some information, some results which I obtained before. And then you need to rewrite this denominator squared. So it will be without square root. So something not quite ugly, but that's okay. We can make these simplifications here. So we end up having x squared plus y squared plus z squared. This guy will give us minus x squared, which means that x's get cancelled out. Okay, but what about the denominator? Denominator will be this guy times the square root of the same guy. It means that this guy will be to the power of 3 over 2. So finally, what we have finally, maybe it makes sense to rewrite it. So r prime prime xx is equal to this expression, y squared plus z squared divided by this expression to the power of 3 over 2. And luckily, our function is symmetrical again. That is why we can easily write r prime prime y. We can just look at the symmetry and realize that if you have x's here, there are no x's here. So in our case, we have no y's here. It means that no y's here. It should be x squared plus z squared. And denominator is the same, of course. I'm even lazy to write it. I'm writing like this. And the same goes for the last partial derivative, r prime prime zz. So no z's here, no z's here, of course. X squared s squared, and the same guy in the denominator to the power 3/3. And now what can we do now? We can just look at these three equations and add them together. Just add them together. Let's try and do it. So the first, the left-hand side of our resulting equation will be the sum of these three derivatives. R prime prime z. And here we have, what do we have here? You can imagine that you will have the same denominator, which is x squared plus y squared plus z squared to the power 3/3, 3 halves. And as for nominator, you will see that every variable gets doubled. So, for example, you have y squared here plus y squared here. It will be 2y squared. And the same goes for the remaining variables. So it will be 2x squared plus 2y squared plus 2z squared. And finally, you can see that you can pull out 2 out of this expression. And inside the expression, you will have r squared. So it's 2 times r squared. And here you have, again, you have r cubed. So finally, these r's get cancelled out, and you will end up having 2 divided by r. I think it's better to rewrite them. Once again, this nice relationship between the second derivatives. So it's 2 divided by r. So this is our second beautiful relationship between our derivatives. You know what? You don't need, the beautiful thing about it is that you don't need to repeat these calculations all over again. You need just to write them out to your cheat sheet and just use them. So let me rewrite the previous equation, previous relationship, so that they could be in one place. So r times z squared was equal to 1. Do you remember this first relationship? And so I recommend you to write out these two equations, these two relationships on your cheat sheet for your exam, for test 2. And you don't need to derive them every time, like I just did for you before, because I wanted you to realize how they could be obtained, this relationship. Maybe this is more of a topic for lectures, actually. So maybe I suspect that I repeated your lecturer's derivations of this formula. Okay, so now it's time to do something really concrete. And the third topic, the third subsection of this tutorial will be solving problems. Solving problems which contain this function r. Solving problems. So when you solve the problems, you will be given function phi, the typical function of 3 variables. It's not function, actually, it's a scalar field, 3D scalar field, as you remember. But of course, besides, you will be given this function r, which is square root of x squared plus y squared z squared. In some cases, you are explicitly given this assignment. But in some cases, you just need to realize yourself that it would be very convenient to use notation. So this is given to you, function is given. And what you need to do, you need to find find Laplacian of this function, which is denoted by nabla squared of phi. You know what? The Laplacian, this is a very short notation, very convenient notation, but it could be written as phi prime prime xx plus phi prime prime yy and plus phi prime prime zz. So that's how your Laplacian could be rewritten. I'm using this shorthand notation, not d squared phi divided by dx squared. It looks a little bit scary. Okay, so let's begin with some problem from our tutorial sheet. I think that the best problem is actually which one? It's the problem. I can find it in my preparation tutorial sheet. Where is it? Why did I lose it? Very frustrating. No. Sorry for this delay. I wanted to give you, very simple example as the first one. Yeah, this is a question 5a. Okay, I found it at last. So question 5a. In question 5a, you have a function phi is equal to x squared plus y squared plus z squared. Nothing fancy, very easy function. And you are not asked to use this notation, which is function r. But you know what? Nevertheless, I'm going to do that to demonstrate you how beautiful and convenient this is. And besides, it allows us to get an extra practice. Why not? So I forgot to write down the assignment. So assignment is to calculate this Laplacian. So we realize that we need to calculate the second derivatives of our function. But you know what? We decided to do this notation. We decided to denote this expression as r. And in this case, our function will be written as r squared, of course. Looks much nicer, of course. But you need to realize that your function becomes like a fancy function. Phi is dependent on r first, and only after that your r is dependent on x, y, and z. So you need to take this diagram into account. But okay, but nevertheless, we need to start with the first derivative. So step one is to calculate phi prime x, and a, y, and so on. Okay, what about phi prime x? You can see this path. So your beginning is function phi, and you can get from this point to this point. Your journey consists of two sections. That is why your chain rule will consist of two terms. So the first term will be phi prime r, because this is the first leg of the journey, times r prime phi. Oh, prime x, sorry, typo. Okay, and let's try and calculate something. So you can see that phi is a very simple function. And if you want to take derivative with respect to r, it will be just 2 times r. So this is our first derivative. And with the second derivative, let's not substitute anything for it. Just rewrite it. 2r times r prime x. And of course, immediately, thanks to the beautiful symmetry which our function displays, we can rewrite all the other derivatives quite easily. So let me rewrite first this first derivative in one row. So phi prime x turned out to be 2r times r prime x. Okay, the second derivative will be written quite easily. So all you need to change just to substitute x with y. So 2r times r prime y. Something this becomes blurry again. And the last derivative, phi prime z, will be 2r times r prime z. So this is our set of derivatives, the first derivatives. Okay, but now we need to perform step 2, which is about the second derivatives. And how do you deal with the second derivatives? Let's start with phi prime xx. Let's recall the definition. Definition says that you need to take the first derivative with respect to x, and then take one more derivative with respect to x. Let's substitute phi prime x by this expression first. I like to use brackets. So 2r times r prime x. So I need to differentiate this equation which is inside brackets. In this case, you need to use another property of derivatives about how to differentiate the product of two functions. So let me remind it to you. U prime v plus u times v prime. So this is our u, 2r is our u, and this is our v. So let's apply this rule. So we need to differentiate the first term, 2r prime x, times the second term is unchanged, plus vice versa. The first term is unchanged, which is 2r. And now we need to differentiate the second term, prime x. So maybe it was too much to write these brackets. It's better to use parentheses, of course, but it's too late. But when you now you need to differentiate this and this remaining expression. But looking at this expression, you should memorize. You should remember all the times, at all times, that r is not just an easy function. R is dependent. R is dependent. No. This function, not R, but this function, this internal function, is dependent on R first. And after that, it's only dependent on, so this function 2r is dependent on r, of course, and only after that it's dependent on x. So you need to apply the chain rule here. So you need to take derivative of this function with respect to r, and only after that you need to multiply by r prime x. So this is the most difficult part probably. So this function should be differentiated in this way. And as for this term, I'm just rewriting it. So this r prime x was here, I'm just rewriting it. So this is the most difficult part probably. Okay, let's move to the next term. So 2r, I'm reading it, and this is according to definition is r prime prime xx. So we need to sort out only this green term. So what is the derivative of this expression with respect to r? Of course, it's just 2. And these two guys, they can be written as r prime x squared. So maybe I even should put green color here. So this, no, it's not a good idea because it's only about this one, red color. So this guy turns into 2, just like this. Okay, so I'm rewriting the second term, 2r prime prime x, and that's it. This is our second derivative. And of course, I'm running out of paper as usual. That is why I think it's better to rewrite my result in this separate page. Okay, so what I obtained here, phi prime xx 2 times r prime x squared plus 2r times r prime x sorry, r prime xx. Sorry for a second, I made a mess here. And as for remaining second derivatives, no problem, it's just a piece of cake. Just look at this expression and use the symmetry. If you have x's here, it means you have x here and x here. But now we have y's here, it means that all the x's should be substituted by y. As simple as this. So r prime y squared. And the second term is 2 plus 2r times r prime yy. And similarly, phi prime z should be written in the same manner. R prime z squared plus 2r times r prime z, and that's it. So we have a set of 3 expressions, and you know what? If you look at the left-hand side, you're like, if you add these 3 things together, you will get your Laplacian. Yeah, you will get your Laplacian, which is nabla squared of 5. So it's already our result. And all that is left for us to do is to do the same, to add up together the right-hand sides. But you can do it term by term. So for example, let's have a look at these first terms. This yellow, yellow, yellow. So how can they be written? If you add them together, you immediately see that you can pull out this 2, and inside the parentheses you will get this inside the brackets better, r prime y squared plus r prime z squared. So this is, according to our nice formula, it's just equal to 1. Do you remember our first formula? Okay. What about the second? Let's denote them as green terms, for example. If you add up together these green terms, you may be able to pull out 2r, and inside brackets, I have to rewrite them here. You will have the sum of these second derivatives, r prime prime y plus r prime prime z. But according to our second beautiful formula, which was written somewhere before, I can't find it anymore. No, it's here. It was in one of the previous pages. Do you remember we explored our function r first, and we obtained this beautiful formula. So now I'm using this beautiful formula. So according to the second beautiful formula, this whole expression is equal to 2 divided by r squared. So it looks like we already we can simplify our Laplacian already. So maybe even the previous page was enough. So Laplacian is equal to what? 2 times 1. Okay, 2 times 1 plus we had 2r here, 2r times, and this guy turned out to be equal to 2 divided by r squared. This should be definitely simplified. This the first term is 2. Here you have something is wrong. It's not r squared, it's just r, sorry, just r. I didn't use my beautiful formula combination. Just 2 divided by r. So r's get cancelled out, and you have 4. Also, the answer is 6. For this problem, the answer is 6. Of course, you might, looking back at this, my solution, you might find it a bit scary, a bit bulky. But you know what? Of course, as for this particular problem, you could solve it in another way. You could solve it more explicitly, just finding all these partial derivatives, the second ones, in an explicit way. But you know what? Unfortunately, some cases, as I told you before, they specifically tell you that please use this notation r. Please give us a result, your answer in terms of r. And this is, in this case, you will find yourself in trouble. So we can view this problem question 5a as a good training, before switching to a real task. When you are asked, you're required to find your Laplacian using this r function. So let's do another example, which is already more explicit. Okay, so this was question 5a, and the second example, I can find it again. Absent-minded. Yeah. This is question 5f. So question 5f, let me write it in green. Question 5f. So in question 5f, you are given function immediately in terms of r. Look at this, e to the power of minus r. And of course, they explain to you that r is equal to x squared plus y squared plus z squared, but you should know already. So if your assignment is given in terms of r, that means that your answer should be given in terms of r as well. This is like a convention among mathematicians. And if you look at the answer to this problem in your tutorial sheet, you will see the answer in terms of r. So here you have no escape. You should use this technique which we have just practiced before. Okay, but now we have still some experience. That is why it won't be so difficult to deal it the second time. So step one is about finding the first derivative. You will never be able to find second derivatives without finding the first derivatives first. Okay, so the first derivative is phi prime x. How can we find it? We should remember that this function is not a simple function. It's just a combination of two functions. So phi is dependent on r, of course, and only after that r is dependent on this x and y, z, as you can see from this notation. So we need to apply the chain rule again. And look at this diagram. We will see a very similar diagram. So we start our journey in phi when we want to find this derivative, and we need to end our journey here. So our journey contains two sections. So it will be chain rule: phi times prime r times r prime x. Okay, and we can substitute phi phi prime r, which is minus e to the power of minus r. And as for the second term, we just rewrite it. I'm not going to discuss how obtain this result, how I differentiate this function with respect to r, because I'm assuming that you already know all these techniques. Okay, and now we can rewrite it in one row. So phi prime x is equal to this expression. I'm just rewriting it to make things more convenient. And as for remaining two partial derivatives, you know the technique. We are lucky that everything is symmetrical. So we're just rewriting, substituting x with y in this case. And here we are writing again, substituting x with z in this case. So we have a set of our first derivatives. Now the step 2 will be to take second derivatives of these resulting expressions. So let's call it step 2. Step 2. So we need phi prime xx. According to the definition, we need to take the first derivative here and differentiate it once again. So let me copy this result for phi prime x, and I'm putting into brackets. So this result was like this, minus e to the power of minus r times r prime x, and I need to take the one more derivative with respect to x from this equation, from this expression. Okay, so what should I do? Again, this is a product of two functions. Do you remember, this is our u, the first function is u, and the second function is v. According to the rule, special rule, we need to take the derivative of this function, minus e to the power of minus a, with respect to x, by the way. I'm trying to be very careful. And we are rewriting the second term, r prime x gets rewritten. Then we need to rewrite the first term, which is this, and take derivative of the second term. So this is my template. And now I need to take these remaining two derivatives very, very carefully. So this guy is very easy, very straightforward one, of course. This is just r prime xx. But for this one, you should be very, very careful with it, because this is a combined function again. So the external function is e to the power of something, internal function j is r, and then again you need to realize that only after that r is dependent on x. So that is why I'm going to do this part in very much detail. So first of all, you need to differentiate this with respect to r, and only after that you can differentiate r with respect to x, and this guy gets rewritten. So again, it's so important that I'm highlighting. So this term should be differentiated in this way. So it's a chain rule for this function. You should always remember that this function is a complex function. This function is dependent on r, and then r is dependent on x after that. Okay, but the second term is much easier, and maybe it's better to write minus already here, because it's minus e to the power of r, and this guy is r prime xx. So again, and now we need to sort out this. So the derivative of this function with respect to r is again exponent, but this minus gets cancelled out. So it will be r to the power of minus r. And these two guys will give me r prime x squared, of course. So of course I'm going to highlight everything. So this derivative corresponds to this expression. So that to make things clear for you, minus r to the power of minus e to the power of minus r prime xx. Okay, so I'm done with the first derivative, and as usual, maybe it's better to rewrite them on one page. Okay, so in one place. So I'm going to copy my first result here. R prime xx is equal to this expression. I'm just rewriting it. Rewriting. Maybe it's better to pull out e to the power r. Yeah, it's a good idea. So let me pull out. I don't know if it's a good idea or not. Okay, I'll do it. E to the power of r, and then inside brackets I can rewrite this expression. Looks a bit nicer in my view. Okay. And so as for remaining two variables, not variables, but two derivatives, we can use the symmetry again. becomes blurry from time to time. I don't know why. So you just substitute x's by y's. So e to the power of minus r. Here you have r prime y squared. This minus r prime prime y. And finally, the last second derivative will be respect to z. So we just substitute y with z this time. Minus r prime prime z. So we have the set of three second derivatives, and now all we need to do, we need to add together these three equations. The left hand side will give us just nabla, not nabla, but Laplacian, sorry, nabla squared phi. And then we need to add up together the right hand side. So e to the power of minus r is still, in front of this expression, and let's add together this expression. The sum of these three expressions will give us our nice formula 1, which is equal to 1, if you remember. So this was our first beautiful expression. Then minus, and if you add up together these expressions, you will have the second beautiful equation, which gives you 2 divided by r. So that's it. So this is our answer. So as you can see, nothing fancy, but as usual, it needs some practicing, because if you don't have enough experience during test and the exam times, you will not just have enough time to do it. You need to get the hang of it. You need to get experience. So my recommendation would be to solve all these problems in your tutorial sheet, especially the ones which concerns this variable r, just to get some practice. And if you feel that even this is not enough for you, I think that there are two more problems there where you can apply this method. But please go to the study guide and find more examples there. Okay, so that's it for today. So we are finished with tutorial 7.